Okay, welcome to my new video, dear students. Today I am going to explain a new concept. Before going to that concept, I need to ask you some questions. Okay, so let us consider the situation where we have this surface like this, and we have the electric field lines which are passing through this. Okay, so what is the quantity of electric field lines which are passing through this surface whose area is A? And we already know the number of field lines passing through the surface area is represented by electric flux phi. Okay. And here the formula for that is given by phi is equal to electric field E into the area through which it is moving. Right? This I have already explained. If in case this electric field line is making an angle theta with the direction of the area vector, this is the direction of electric field. Okay, so this is the direction of electric field and this is the direction of area vector, and E is making an angle theta with dA, then flux phi is given by E dA cos theta. Okay, then phi can be written as E dot dA. Okay, so this is one formula that we have here, and if you want to find out the total flux, that can be written as integral over E dA. Okay, this also we can use. What if we have a closed surface, a sphere like this, and we have a charge inside this? Let's consider that the charge is Q. What is the flux through this sphere? Here the charge is enclosed within this three-dimensional sphere. What if we have a cube here like this, and there is a quantity of charge inside that, and what is the magnitude of electric flux which is coming out of it? So what is the formula for that? What is the formula for phi? That is what we are going to learn today. So we have the Gauss law, dear students, and its statement goes like this: the total electric flux over a closed surface is equal to 1 by epsilon naught times the total charge enclosed by the closed surface. Here we have dealt with two different scenarios. One is a open surface. This is a normal surface, okay, and through which the electric field lines are moving. This is not closed one, and for that electric flux is this. What if we have closed surface? Then how will you find out phi? So I will find out phi from Gauss law, that is phi is equal to 1 by epsilon naught times into Q. So here, according to this statement, the total electric flux is represented by phi over a closed surface equal to 1 by epsilon naught times the total charge enclosed by the closed surface. So that is phi is equal to Q by epsilon naught, where Q is the net charge inside the closed surface, not the charge outside the closed surface. Do remember this. This is very essential while solving the numerical part. Simple statement. So this is Gauss law. Okay. So by using this, we will solve the numerical problems, conceptual problems, and illustration problems. Okay. So this is very essential. And from Gauss law, we can find out the electric field also for continuous charge distribution. We'll solve that. So before going to that, solving numerical problems and all, let us take a time to understand this, and how is there any proof for this? Is there any explanation for this Gauss law? Yes, it is. we have this, that is proof for Gauss law. Actually this is not the exact proof for Gauss law, but it's a kind of example for explaining the Gauss law, and we will get the final answer for electric flux as q by epsilon naught. So here I am considering this sphere, three-dimensional one. Suppose the surface S is a sphere of radius small r centered at q. That means we have a sphere whose center is at q, and we have charge also, that is q. Since we have the whole charge is here, then we can consider this sphere, surface of the sphere, as Gaussian surface. Gaussian surface is the imaginary surface considered to apply Gauss law. Okay, so we can apply Gauss law for this surface, but we are going to prove that, right? Okay. Here I have given the statement for that, or the definition for that. Any closed imaginary surface considered to apply Gauss law is called Gaussian surface. So here if you consider the electric field radially directs outwards, and the electric field at this particular point is given by 1 by 4 pi epsilon naught q by r square. And if you want to find out the electric field at this particular point, here also it will be same, because so this distance will give you the radius, and electric field directs outwards at this particular point, and you will get the same magnitude of electric field. Then the electric flux through this area, that is, let's consider df through this area ds, is given by df is equal to E into ds. So this is in dot product. Actually it is a scalar quantity, so E dot ds, that is equal to E ds cos theta. What is theta here? Here theta is the angle between electric field and area vector. Look at this, the electric field and area element are directed outwards and parallel, so that's why theta is equal to 0. So if you consider any point, so let's consider this point here, the area will be directed radially outwards like this, and that is parallel to this electric field, dA or ds, whatever it may be. Here they have considered ds, let's consider ds only. So ds is parallel to E means the angle between the ds and E is 0, so we have theta value as 0. So cos 0 is 1, cos 0 is equal to 1. So we will get E dot ds cos 0 is equal to E dot ds, or E into ds. Okay, so total flux through the surface is given by phi is equal to integral over df, because this is the flux through this small area ds. If you want to find out the flux through this whole surface, because electric field will be moving radially outwards in this particular direction, like this, here also, here also, here also, in all directions it will be moving. So the total flux is calculated by integrating this df. So total flux phi is equal to integral over df. If you integrate this, what do you get? So that is what we are going to find now. So here we have phi is equal to integral over df, that is equal to, we know what is df, df is E dot ds. So integral over E dot df, that is equal to, if E is constant, because R value is constant, E value will be constant. So integral over ds. What is integral over ds? That is the total surface area. What is the total surface area of the sphere? That is pi r square. So this E value is this one, 1 by 4 pi epsilon naught q by r square. And what is ds? ds is small area. What is s? S is the total surface area of this sphere, this whole surface area of the sphere. So we know the formula for surface area of the sphere, that is this 4 pi r square. So here 4 pi r square will get cancelled with this 4 pi r square. 4 pi into 4 pi will cancel out, and r square and r square will cancel out. So we will be having q by epsilon naught. This is Gauss law. This is Gauss law. Okay, so this is the proof, or this is the explanation that we consider for the proof or for proving Gauss law, right? So what is Gauss law? Statement of Gauss law is the total electric flux phi over a closed surface is equal to 1 by epsilon naught times the total charge enclosed by the closed surface. So phi is equal to 1 by epsilon naught times the total charge enclosed by the closed surface, not open surface. Do remember that. So Q by epsilon naught. Okay. So then we have the applications of Gauss law. In that, the first one is we have the derivations for this. So I'm not going to do that in this video. In the next video, I'm going to derive these expressions. Now I will just show you that what is the expression for electric field that we have found by using Gauss law. So first application is electric field due to an infinitely long uniformly charged wire. We can find the electric field due to an infinitely long uniformly charged wire by using Gauss law. So from that we can get E is equal to lambda divided by 2 pi epsilon naught into r n cap. This is in vector form. And what is lambda here? Lambda is linear charge density. R is the distance of this particular point from this wire, perpendicular distance. Okay, and pi is 3.142. Epsilon naught is absolute permittivity, and E is electric field. N cap is unit vector. Then the electric field due to a uniformly charged infinite plane sheet is given by E is equal to sigma by 2 epsilon naught into n cap. So this is also found by using Gauss law. So there is a derivation for this also. I will explain this in next video. So here we have a plane sheet on which the charge is uniformly distributed. So what is the electric field moving through this? That we can find by using Gauss law. So from that we will get E is equal to sigma divided by 2 epsilon naught. Okay. Then we have the field due to a uniformly charged thin spherical shell. Okay. So in this we have three different cases. First one is when point P lies outside the spherical shell. Here we have the spherical shell. So this one is uniformly charged. Okay. Uniformly charged. Now, what is the electric field due to this spherical shell at this particular point P? So here I am considering a Gaussian surface. This is the Gaussian surface that I have considered. What is the electric field here? So that is given by 1 by 4 pi epsilon naught q by r square, where r is the distance, q is the total charge enclosed by this shell. So then when point P lies on spherical shell, so then this r, the distance of this point r will be equal to this radius of this sphere. Then we will get E is equal to 1 by 4 pi epsilon naught q by, in place of small r, we will get capital R, that is equal to radius of the sphere. So E is equal to sigma divided by epsilon naught. So then here sigma is equal to q by 4 pi r square. Okay, so this is surface charge density. Okay, so then we have when the point lies inside the spherical shell, the charge enclosed by the Gaussian surface is 0 inside the cell, because we consider the charges which are present on the surface of this spherical shell. So inside there will be no electric field. So this I am explaining, so you can make a note of it. So these formula are very important for your competitive exam point of view. So that's why I'm explain the main formula here. So the main thing that you have to do is making note of all these important points. So in the next video I'm going to derive these equations. So we'll meet you in the next video. Till then, take care. Bye bye.